the idea was to compute volumes. Well, first understand the volumes best we can under the circumstances in terms of, rather than 3 measurements, in terms of 2 measurements. So just as the area is understood in terms of the measurements of the width and the height, the volume is understood in terms of the 2 measurements, the area of the base and the height. Okay, so the reason why we choose to treat it this way is, we'll see in a minute, you probably already can see it here. What is happening is when we move to the next step, rather than dealing with the rectangular objects, but when we deal with a curved object, and when the objects are curved, then we have to slice them up. And when we slice them up, it is a good idea that we only will be looking at the areas, and then see how those areas vary as we progress through through that solid. So as an example, I have my solid like this maybe, and what I do with it, I cut it with a vertical. I align it along a straight axis X, okay? And then I have actually 3 dimensions here like this, and I start cutting them with planes that are vertical, and so they will look roughly like this, okay? And I will be cutting out of my solid something like this maybe. Okay, and I will be following whatever is happening to those cuts, to the areas of the cross sections, like this. Okay, so once again, a plane, a solid is hanging, floating in the air. Okay, then I choose where my x-axis is nearby, and then I place a vertical plane on that horizontal axis. So x-axis here, vertical plane is placed on top of it, and then I see how that plane cuts my solid. Okay, and then I will be moving along the x-axis with the plane moving from left to right. So there will be a bunch of them, and every time I move, I only care about one thing. I don't really care about the shape of that cross section. I only care about its area. So I will be tracing those areas, and from that I will deduce my my volume. Okay, so I want you to see that the story is repeating itself. We had something similar very shortly before. So imagine we're going down from the 3-dimensional situation of solids and their volumes. We're going backwards to 2-dimensional situation with areas. So what I might be talking about is something like that. So I have this is not a solid, this is a 2-dimensional region. So this was like, if you like, I could try to make it look like it is 3-dimensional. So this is the one on the right is on the left is definitely 3-dimensional. Here I want to talk about once again 2-dimensional situation. So it's a region. It's a region on the plane. And then how do I find its area? Well, once again, I have my x-axis over here, and then what I do is I pick lines parallel to the y-axis like this. Okay, and then in each location I look at the cross section. Okay, and what I care about is its length. The length of that cross section will be varying as I move through the x-axis. So there will be more like this. Okay, so every time I have an area, and that area, what do I do with those? Those area lengths. So I'm going through these lengths. Okay, and then what is the area? What is the area of the region on the right? In terms of those lengths. Imagine that I'm slicing not in a continuous manner, but in intervals. Okay, so then well, then my area on the right is split into slices, and the area which slice will be the width times the height, and the height is that length over there. Okay, so it will be the sum of what? Of the areas of what? Come on, area. Of the areas of the slices. Okay, sum of the area of the slices, in each of which is equal to the width times the length, which is the same as height. So what I'm talking about is this is my length. Well, let's take this one. This is my length, and let me make it thick to make that point. So it's fairly thick. So this is my width. So it's very much what we have been talking about just one day ago, right? The width times the height gives me the area of the slice. I take it together, give me the whole area. If I go that amounts to other even sum of what? Of f minus g. If f gives me the upper edge of my curve and g gives me lower edge of my curve. Okay? When I take the limit, Riemann sum turns into what? A limit with making those slices thinner and thinner. What does it give me? Riemann sums converge to what? The area, also known as the exact area. So Riemann sum approximates the area because if you look at it, it will still look like this. The area that you're approximating looks like this. Okay? But if you make that little delta x go to 0, then the whole thing, the approximate area becomes absolute, accurate area, and the end result is the Riemann integral. Of f minus g. So, integral f minus g dx from a to b. Say this might be a, and this might be b. Okay, so that is just a review of what we have been doing, computing areas in terms of lengths. So that's the thing about it. The length varies, and that's why you have to carry out this non-trivial operation of integration in order to find the whole area. But otherwise, it's very familiar, and we want to bring this understanding. Well, let me first bring up what I already talked about a few times, but I always didn't have a good picture. So that's a better picture about how one could compute areas, areas of a region that is determined by an upper edge and a lower edge. Okay, so the point here is that it doesn't matter what the these are the same pencils. So I have arranged the pencils on top with some fairly smooth edge on top and somewhat rugged edge at the bottom, and so it has an area, right? But then what I did is so I moved these pencil up and down. What has happened is not a big deal. The area is the same. So the value, whatever the exact edge of top and bottom are given, is not important. What matters is the length of those pencils. Okay, so that is f minus g is what matters. When we compute it, we move to f minus g over here, we'll forget what f is and what g is. We only care about what their difference is. So the lengths of those pencils, the pencils, if you want to see those pencils, this is where my pencils are. Okay, only their lengths are important. I could move them up and down. That would make any difference. So the lesson that we learn from here is that the area is determined by the cross sections, the lengths of the cross sections only. once again. So the area is determined by the length of the cross sections, period. So just like our picture indicates, also certainly the formula helps. At the bottom, you can see that only f minus g, the length of the cross section. That's the length of the cross section. The only thing that matters. Okay, so that understanding we want to bring to our three-dimensional case, and think by analogy. Okay, so instead of pencils, what I have, think coins. Coins. Okay, so these are the colors slightly different, but these are the same coins. Okay, so each of them has a cross section and it varies. However, I could rearrange them, put them in any other shape, and the volume remains the same. It's the same coins, right? So the coins on the left, coins on the right, I just may straighten them out a little bit more. Okay, so so what hasn't changed is the cross sections, right? So it has the same height. On the same height, I have the same exact coin. So the cross sections coincide, and as I move on, even though these cross sections move left, right, as you can see. The same coins, but located differently from each other, from left to right. Okay, but they will adapt to the same volume because, well, these are the same coins. So the idea that we had on the left, made of pencils, made an area covered by pencils. No matter how you arrange those pencils, as long as you move them just up and down, the area will be the same. Similarly, here, if I move those coins side to side, what's going to happen? Nothing. The volume won't change, and why? Because the area doesn't change. Okay. So let me just write it out here. The volume is determined by the cross sections of the solid. Okay, the cross section is chosen in one particular way. I could certainly cross stack it in the horizontal planes if I want to, but the way we're arranging the whole thing is analogous to what we did in the two-dimensional case on the right, and so we will be crossing with planes perpendicular to the x-axis. Okay, so that will make the whole thing only will have only one parameter. Okay, so one parameter being x, just like on the right, the cross section depends on x, period, and then you integrate it. And the exact same thing is going to happen with the volume. The cross section varies depends on x only, and so then the volume will be simply the integral of what of the areas. Okay, so if I integrate, so let me explain this one more time. Here, this is the length of the cross section. And we integrate it, we get the area. Similarly, the answer will be for our volumes. So that's the area. Volume. Integral from A to B once again, but this time I'm not going to, there are no two functions. That will be something of a challenge to represent, properly represents, somehow create a boundary of that solid in an algebraic fashion, but we will. At this point, we'll just say AX dx. And this is the area of the cross section. Of course, it depends on x. This is a particular value of x we choose, and above it, just like over here, we choose something to cut the object with. So either a line on the right, we cut with a plane on the left. But as you can see, the computation will be very similar as long as we are able to find that area function x, ax. We will be able to find the answer for the volume by simple integration. Okay, so one more, I guess, in order why this works out on the left. the plan is once again similar to what we have on the right. The slicing produces the cutting produces slices, just like we have over here. Okay, and the whole thing, this is horizontal, and we prefer it to do in a vertical fashion, but they adapt to the whole volume. They approximate the volume, and then we already know how to find each of those slices. This is A of x. A of x. So the volume here of this little, it's a disk. I mean, it doesn't have to be a disk, but because we don't really care. This is delta x. Okay, so then the volume is AX times delta x. Okay, so each slice will have this this volume, and then the total volume will be the sum of these. Sum AX delta x over the whole thing, okay, and over a partition of our integral AB. And once again, as we take the limit with delta x going to 0, we will have the exact volume, not the approximate value. So I'm not going to go through a lot of details here, but we already did enough with the area. So as far as the Riemann integral is concerned, it is the same Riemann integral. Okay, so look at it. It's still familiar Riemann integral on the left or on the right. The only difference is the challenge is finding that area function. Okay, so on the right we are able to find almost any area imaginable, any region imaginable in that manner. All we need to do one function and the other function. Not so easy with volumes. So we would have to actually to reach the same degree of proficiency for finding volumes, we would have to be able to define surfaces rather than curves. Okay, so we will have to wait until calculus 3. So defining surfaces as functions. So we know how to define curves as functions. Okay, that we can do. Surface is not so easy, but some of the objects at least can be handled. It can be described geometrically as, for example, it could be a cylinder, it could be a cone, it could be a sphere. All of these can be then we can figure out the areas of the cross section for those geometric figures based on our understanding of geometry. So we'll do a couple of examples of that. Let's start with the one that we already know the answer for. Let's confirm that the formula that I have here at the bottom left matches what we discussed yesterday. So, for example, this picture primarily I want to well, yeah. Let's look at the cylinder. Area of the base times the height. So there is no integration involved. We just take our understanding of what's going on, and just in fact there is a formula for the volume of the cylinder, which comes in unexplained, and only right now at least we're making step in that direction to actually justify such a formula. The formula of a cylinder, the area of a cylinder is area of the base, which is pi r squared times the height might be h. So 2 pi r squared here, the bottom, the area of the base, and the height is h. Okay, so that is our understanding of from geometry. We know the answer. We don't know where it comes from. Now at least we can somewhat explain it. So let's do that. So so find the volume of a cylinder of radius r, height h. Okay, so once again, even though we plot it usually like this, standing, well, we're not going to do that. We're gonna put it on the side so that it will match our pictures from before. So I'm gonna put it like this. So this is like this cylinder. Maybe like this. Yeah. Okay. So that's my cylinder. along the x-axis. Okay, so let's now identify the items that we're going to need for our computations. They are for the firstly we're going to need A and B. So let's say this will be H. So it is a cylinder that is, well, let me complete the circle here like this. Okay, so so it's located between 0 and H on the x-axis. Right, so that is my intro. It remains here. That's my intro from 0 to H. Okay, and then we don't really care about the geometry. The three-dimensional geometry is out. We don't care about it. All we care about is the area of the cross section. So to apply the formula, now find the area of the cross section. Cross section with a vertical plane. So in other words, this is the plane I'm talking about is like this. It would be one plane, and then the next one maybe here, like that. Okay, so that will be my cross section right there. This is the cross section that I care about. So what can you say about the cross section? It's a circle. Which circle? So it's a circle. What kind of circle? Well, not what kind. We actually know its radius. What's the radius? It's still R, right? Because by design, right? We certainly, you can take a cylinder and cut it like this, but we don't do that. We cut it the way we want it. So it has a our cylinder has the height perpendicular to its base. Okay, so this is, if you like, this is a right triangle right here. Okay, so the base is perpendicular to the height, which means that if we keep cutting it like this, we will produce the exact same circle every time. So it will be radius r. Okay, so x is pi r squared. That's all. Okay, so every cross section is exactly the same. It is pi r squared, and that is our function to be integrated. So now we use the formula. So our volume is integral from 0 to h, ax dx. Well, let me put ab here to begin with. Now we substitute integral from 0 to h, b, pi r squared, d what? d dx. It's not dr. Why? Because r is not changing. So, and as we're moving along x, apparently there is no change of our cross section. There is no change of our area function. So, well, it turns out the function does not depend on x. It's a good news, certainly. So, what's the answer? What do you want 1/3? No. R does not depend on x. So it is a constant function. So how do we integrate constant functions?
It's just pi r squared.
So it will be pi r squared. Well, you don't throw out the integral altogether, right? So pi r squared, what do I have here? What's the integral of dx? It is the 1 there. Integral? It is, no, integrate 1, you get x. So it's x from 0 to h, right? And then that's how we get pi r squared h. Okay, so that you can see what can happen if we pick a more complex example. What's going to happen is simply the area function is not going to be constant anymore. So any kind of shape you pick, probably it's not going to be constant. But you can think of, for example, when it is easy constant, for example, if it is a box or anything all that manner, you can imagine many shapes that have the exact same cross-section. So it doesn't have to be a circle, it could be a square, it could be a rectangle, it could be a triangle, okay? And then you know what's going to happen is you just take that area, which happens to be constant, and you just multiply it by height. So triangle, and I'm producing a volume like this. A triangle, a volume, it's a prism. I think the word for it is a prism. So the base is triangle, and then that triangle is repeated in a vertical direction the exact same way. What's the volume? I take the area of the triangle multiplied by the height. That's it. That based on this formula. It could be what could it be? Any I don't know, an ellipse. Also, start with an ellipse, translate it vertically. What's the volume? The area of the ellipse multiplied by the height again. So that's what happens every time the cross section doesn't change. Okay, so it is simpler than what we want to deal with. We want to certainly look at examples that are slightly more complicated. So let's do the sphere. Let's do the sphere. So radius r once again. So that's what we started with anyway. So it's a good motivation for us to follow on with because it's like we just recently computed the area of the circle. Now what's the next step up is the volume of the sphere. Okay, so the idea is the same. So we'll be doing cross sections, right? So I may have a picture here somewhere. Okay, so that is the illustration of what we talked about. Equal cross sections produces equal area, but that's not what I have in mind. I'm talking about a sphere. Well, you can imagine, so I don't have to plot it. You can see what happens if we start to cross-sect a sphere. You see what's happening? What do you see? What can you say about the cross-sections? It is changing, yes, but they are all, what's the shape? It's a circle, so you cut the sphere, you get a circle. Yeah, inevitably, no matter how you cut it, you always have a circle. In this particular case, we're cutting it in a parallel fashion like this, and what you see here is several cuts as x moves from left to right. So in fact, the one is missing on the way on the left. It's still a point. So start with a point, small circle, bigger circle. In the middle, it's the biggest circle that it coincides in the radius with the radius of the sphere, and then it starts to decline again until it disappears into a point again. Okay, so at least the picture is more or less straightforward, but we actually have to, that's not enough, because we need to know exactly the area function as it depends on x. So we have to figure out, this is what I'm talking about is, say, let me try to illustrate that. Okay, no, not working too well. So what I'm talking about is, say maybe these are x's. Well, it depends on where you want to put my sphere, but I certainly will put sphere in the middle of my universe. So it will be located relative to the x-axis in the middle. So the center of the sphere will be at the origin. So this could be x. So the radius, say radius is 1. Then this might be what is it? Negative 2/3 maybe. This is maybe negative 1/3. This is 1/3, maybe, or 2/3, maybe 1/2. And this is what's the value of x here? me try to bring it here. Okay, so what I'm talking about, let's give it let's give it an axis. So like this. Okay. Well, actually, let me start over here, like this. Okay, so these are my axes. X-axis on the left. It continues on to the negative direction as well, like this. Okay, so it will be running between -1, -1 on the x-axis. My interval will be between -1 and 1. Okay, and as you can see, I have four different values of x for different cuts. So this, like I said, could be x equal -2/3. This x equal -1/3. X equal to maybe 1/2. Okay, and this one x equal to 1. Okay, is the cross section when x is equal to 1. Our plane and our sphere only touch each other, and so we end up with a single point. But that's just an illustration. We actually have to take it to the next level and actually illustrate it with we need to figure out the area. So what is A of x? So this is, okay, let's make that clear. This is A of -2/3, A of -1/3, A of 1/2, and this one is A of 1, which happens to be 0. At the other end, by the way, A of -1 is also 0 at the very other end, when also the plane and the sphere only touch each other. Okay, so only one point in common. So it looks more complicated than it deserves. What I'm going to do, because all we need to do is, okay, these are all circles. Say R of x. It depends on x. So we need to find that function. Okay, so if we know R of x, then we will find the area. So after a function A of x, which represents the area of these varying circles, and we need to find the varying radius. And from this three-dimensional picture might be complicated to see it. So what I'm going to do is I'm going to look at the whole thing from the direction from the right, from what direction, I'm not sure which direction it is, but imagine that I put my eye like this. Okay, so that axis points into my eye. Okay, so I don't want to deal with 3 dimensions. So that's what it's going to look like. I'm facing only the x-axis like this, and my circle is this. Well, suppose this is y-axis. Okay, so I want to kill the y-axis. I let the y-axis point exactly in my eye, and if something is pointing into your eye, you don't see it. So the y-axis will not have any effect. Okay, the z-axis will be still visible. That's the z-axis here. Okay, so that is my z-axis like this. This is my whole circle. Okay. This is my sphere. I mean, it looks like a circle, but let's make it clear. This is a sphere. Our sphere. Yeah, I'm afraid okay, I see. The example here in the middle is actually refers to r equal to 1. The radius is equal to 1. So I do want to have the general case to consider. So let's assume it runs between -r and r. So this is our sphere centered at the origin of our three-dimensional space. This is x, this is z. Okay, and now I'm going to be crossing it. I'm going to be crossing it with planes, just the way we did. So, for example, this is an example. Like, where did this circle come from? This is where it came from. It was cut with a vertical plane. Okay, so where's my plane? So let me put it right here, like this. So this is the cutting plane. So once again, it looks like a line, but it's really a plane because we're looking this way, so we don't see it. We see only the line. Okay? So now let me show you my circle. You see those red circles? This is what we see from the circle. So this is the circle. 2 points of the circle. That's also the circle. So when you cut it, the circle turns into a segment. Okay, so this is my circle. It runs between these 2 points. So this is my plane, still red, but really we now interested in this segment, which is the circle visible from the side. Okay? Why do we care? Because there is a radius here somewhere. This is, by the way, is x. So for each x, I have a crossing. I have this circle, and now I can find its radius. So this is still circle. So find its radius. Okay. So can you tell me how we find the radius here? You see the circle, right? That red thick line, it is our circle. So where's the radius? We are looking at this. Let me make that clear. Well, this is what we're looking at. That red, well, let me make it change the color. How about this? The circle is purple. Okay, so the cutting plane is red, but the circle itself is actually purple, and that's what we're looking at. As you can see, the purple one is not the radius. The purple line is what?
Is it proportional to
It's the diameter. It's the diameter of our circle. So if the diameter is just divided in half, we have the radius. Okay, so then equal to 1/2 of the diameter. So if x, you can see x, you also know that this distance is r. It's our circle. So what is the radius? Well, I guess we don't really need this part anymore. So this is, you see the picture? This is the radius. This is r of x, the vertical part. Twice will be the diameter. Okay, the inclined line is our radius of our original sphere, and the bottom is x, which varies. So we can certainly find r of x. Right? What's r of x? From the Pythagorean Theorem. You see the right triangle? Okay, so the 3 sides are, 2 of them are known. Lowercase r is known, and x is known. R of x is unknown, and what we can solve the equation by the Pythagorean theorem. So what do we get? Pythagorean theorem gives me what? R squared minus x squared. Squared, yes. Okay. So in other words, what we got measurements of our cross section, which is all we need in order to find its area. Okay, because it's circle, we know its radius, so we know its we know what we need to know, and which is its area. So a of x is pi rx squared, right? The radius varies, but suppose x was fixed, so there you go. And then it simply will be pi r squared minus x squared. Okay, so we need to know. For every cross section, you can verify that it works out. So test it. In fact, a of 0 is 0, right? I'm sorry, a of what? A on the left and over here, not here, over here, it is a of negative r, and look at it, a of negative r is, look at the substitute, what do I get? Substitute in the formula on the right. If x is equal to negative r, what do I get? It is 0, and the same thing on the other end. A of r is also equal to 0, so we're getting what we want. We can also verify that a of 0 is pi r squared. What does it tell you? So there are two end cross sections. They give you nothing but zeros because there's only touching there on that plane. And in the middle, what does it give you? It gives you a circle. What? What kind? What's so special about this circle in comparison to the rest of them? It's a maximum radius, and the area coincides with the area. No, its radius is the same as the radius of the original sphere, right? So with the picture which is not here, but I could try to plot it for you. That particular cross section is here. So this cross section that I'm highlighting is x equals 0. So see that x is at 0, and when we cross it, we're getting the biggest one. Think about the Earth, right? And we're pretty much talking about we're not talking about the meridians, but rather, well, this would be like the equator, right? So the equator is a circle, and it has the same radius as the radius of the sphere, which is the Earth. Okay, anytime you cut it higher, the latitudes, right? You cut the latitudes. Yeah, that's how you can think about it, except they're in the wrong orientation. But you can think of these as latitudes. Okay, so this would be the North Pole is here, and the South Pole is here on the other end. And you're cutting our Earth with planes when naturally producing circles, except at the very top at the North Pole we have a point, and at the bottom at the South Pole you still have one point. In the middle, you're getting your equator, and it is the largest possible circle. And it's actually called the Great Circle, or there are many great circles, one of the great circles. And its radius is the same as the radius of the Earth. Okay? So that's all just an illustration. Before the algebra is fairly straightforward. Now we have our formula right here. We integrate to find the volume. So volume is equal to integral. Look at the picture. It will be our integral AB is between negative r and r. And I substitute my area here, which is pi r squared minus x squared dx. Okay, so I just go on to integrate this. So it will be, let me take pi out. And I have, so I integrate r squared, which gives me r squared x minus x cubed over 3 from negative r to r. Okay, so I just carried out the integration by the power formula. And what do I get? Pi. And now I substitute, right? So I substitute r. What do I get? R squared times, carefully here, r squared times r minus r cubed over 3. Okay, now I substitute negative r, so I'm going to have r squared negative r plus negative r cubed over 3. Okay? Yeah, I think I got it right. So I substitute r first by the fundamental theorem, naturally, and then I substitute negative r. Okay, so let's, it will be all r cubes all over. So it will be pi r cubed minus 1/3 r cubed plus r cubed minus 1/3 r cubed. Okay, so altogether, I have, what do I have? This is a cube again. Cube. Pi. Okay, which is what? 4/3, right? 4/3 r cubed. The formula that you find in every textbook, so including yours, there are that list of formulas. So we also have the volumes of geometric figures, and that's the volume of the sphere. Okay. So it is longer than necessary. It might be this is the whole problem here. So visualization helps, but not absolutely necessary depending on the circumstances. In this particular case, as you can see, how I guess the result is how nicely the area, the formula for the area of a circle turns into the formula for the volume of the sphere. So that pi r squared that we used over here, in one spot, not here, over here rather. And the Pythagorean Theorem combined together, they produced through integration, produced the formula for the volume. You can also notice that how pi r squared turned into 4/3 pi r cubed, and you can see how how dimensions grow, right? So pi r squared has r squared there. Why? Because it is an area, so it's measured in square feet. Now you can see how we arrive to volumes and have r cubed, so it's measured in cubic feet. Okay, so you can imagine that we are talking about, if we were talking about the surface area of the sphere, then we would be talking about square feet again. And where did the extra r come from? You can point it out. So over here it was still squared, but it was multiplication by dx is what, followed by integration, obviously, that brings the dimension up. So if we had that expression over here has square feet, but this is feet. So square feet times feet, you have cubic feet. Okay, so we're gonna do one more example. We'll do the pyramid. Okay. All right.